Hello everyone. In this lecture we will be solving another application of the Symmedian lines. This problem is taken from the USA team selection test from the year 2007. Here's a view of the problem and a simple sketch as well in the same page. So we are given triangle ABC, and it is known that it is inscribed in circle omega. So therefore this circle right here is circle omega. The tangent lines to omega at B and C, and you can clearly see those two tangent lines, meet at point T, right here. Point S lies on ray BC, so we have the ray BC, and point S, we know it lies somewhere on that, such that AS is perpendicular to AT. AS is perpendicular to AT. Now this gets us thinking, because we already can see by the construction there's a circumcircle around triangle ABC. The tangents meet at T, therefore AT is simply the Symmedian, right? So we are actually, AS is a line perpendicular to the Symmedian line. Let me just make note of this. AT is Symmedian line. Okay, good, so that's perfect. Points B1 and C1 lies on the ray ST. Now we have point B1 and C1 with C1 between B1 and S, obviously, so that's the orientation, the appropriate orientation. And we're also told that B1T is equal to BT, which is equal to C1T. So what I did is I went ahead and did draw this additional circle here. So I hope everyone can visualize this circle. So this circle is our own construction. This circle is not given in the problem, so we decided to construct this yellow circle. Prove that and that circle obviously satisfies these conditions. Prove that triangles ABC and AB1C1 are actually similar triangles. So ABC is the original given triangle. Show that AB1C1 is similar to ABC. One way that can be done is obviously if you can establish some similarity between by just employing some angle chasing would be one option. Another option would be to compare side lengths, which is the way we will do it actually. In addition, what I did draw in the picture is to visualize because I know AT is the Symmedian and I know it must be symmetric to the median with respect to the angle bisector. So I did go ahead and located that midpoint M, which I know very well will be perpendicular. It will be on the the point T will be on the perpendicular bisector of BC, so therefore M will be kind of aligned with that T here. So that observe that special location of M here. So M is the midpoint of BC, AM is the median, so let me write that down as well. So AM being the median is a very important for me. And because now the relationship between the median and the Symmedian, I can immediately establish that, for example, angle BAT is simply equal to angle CAM. So what else? In addition, I also marked two angles here, as you can see. So notice that angle ABT, because it's a tangency angle here, it subtends this arc ACB here. But notice that angle ACB itself subtends the other portion of the circle. So therefore those two add up to, and they are not central angles, so they are on the circle, those two angles. So therefore those two angles should add up to 180, or you can say angle TBA is simply equal to 180 degrees minus angle ACB, or angle ACB. Yes, that would do. So now I can go ahead and, having observed these two results, so those are the two results that I will need here. So those two angles will be very useful. So I will go ahead and follow the same methodology I've been doing for a while I'm proving Symmedian problems. And let's use the law of sines, and let's apply the law of sines to triangle BAT and CAM this time. So I will apply law of sines to triangles BAT and triangle CAM. So try to follow my reasoning here. So BT over AT, I will try to find the length relationship between those two claimed triangles to be similar, right? So BT over AT, by just applying the law of sines to these triangles, will be related to sine angle BAT, obviously, divided by sine of angle TBA. Obviously, I applied the law of sine in this triangle, and that in turn is equal to, well, we just established that BAT is equal to CAM, so therefore their sines should be the same, so sine angle CAM, and then TBA, we just realized it's 180 minus ACB, therefore their sines should be the same, so sine of ACB. Even though the angles are not equal because they are supplementary, their sine function should be the same. And therefore this thing is equal to, now I just apply law of sine on this triangle CAM, therefore this would give me the length relationship MC over AM. Now we need to make this curious observation. So now notice on this relationship that so BT over AT is equal to MC over AM. What I would like to do here is that notice that BT is given to be equal to C1T in the problem. So I will make use of that, so this substitution. So therefore this implies that TC1, so I replaced BT with TC1 divided by AT is equal to MC over AM. And so finally notice also that because it's given in the problem that this angle TAS is 90 degrees, but then later on we also observed that T must be located on the perpendicular bisector of BC, which turns out to go through M and T as well, so therefore TMS is also 90 degrees, suggesting that points S, A, M, and T are cyclic points or concyclic points. So because they are cyclic, this suggests that angle AMS is equal to angle ATS because they would subtend the same arc. So this angle over here, that red angle, is equal to this angle down here. But then that does the trick. So not only we prove that this relationship between those side lengths holds, so let me actually make sure that you guys can follow the relationship between these side lengths. So let me make it a green color for this one. So we have TC1 over AT. So TC1 over AT. So let me have it another color, probably red. So MC over AM. So MC would be up down here, and then AM is just here. So and not only that relationship, but just a few minutes ago I just explained how, because SAMT are cyclic points, those two angles between them are equal actually. So this angle is equal to this angle. So not only we have two side lengths having the same kind of a similar relationship, but also those angles are equal. It suggests some similarity here. So therefore these side lengths being equal, as well as these angle between those openings being equal, suggests that those two triangles, in fact AMC, triangle AMC is similar to triangle ATC1. But then in a similar way one can easily show that AMB is also similar to ATB1 as well. So therefore combining these two results, it implies that triangle ABC is simply similar to triangle AB1C1. So again, combining those two results suggests that those two triangles ABC and AB1C1 is similar, and therefore we are actually done. So hope to see you in our next video.